even though they're adverse at low speeds, we can use the properties of a shock wave to create low and high pressures above and below the wing. And then now we have lift, but you have to go really fast to get it. So that's one thing, is to make the wing really, really thin and kind of diamond shaped. The other thing is to make the wings sweep back. And the reason we did that is at the front of the plane, let's see if I can draw a plane.
Draw it on a bird?
Yeah, it is a bird. At the front of the plane, we give it a very sharp wedge nose. And we induce a shock at the front of that. And the result is a shock that goes, and it's conical, it's three-dimensional. It's called the Mach cone. And if we can keep most of the airplane inside that cone, you can imagine the cone spreading out. And if we can keep the wings inside that cone, then on the other side of the shock wave, we have subsonic. So here we're flying at the speed of sound. It hits the shock, slows the air down, but now it's subsonic, and it travels across the wing as if it was moving slowly. So some things that people do, so in order not to have a rocket launch you into the air every single time, they give the wing a little bit of camber, a little bit of the properties of a slow-flying aircraft, and they keep the wings swept back inside this Mach cone, right? And so then the air travels at subsonic speeds over a curved wing. It's still thin, but it's curved, and they're swept back to keep inside of this conical shape that's produced by the shock that we've induced at the front of the airplane. So you see those airplanes with their wings swept back because they want to stay inside that cone. And when they're going at slow speeds, they bring the wings forward, increase the amount of area that they have so that they can land and take off like a normal plane. And when they go fast, they bring the wings back. So if you don't sweep the wings back, if you keep them back to fly fast, then you have to have really high landing speeds, and that's kind of dangerous. So people like to land slowly, which is when they bring their airplane wings out forward. So here's the shock wave equations. There are a lot of them. And every time you change something, you've got to redo the whole equation. So what we've done is we've gotten really good at taking equations, putting them into a computer, and then we say to the computer, oh, change this little thing. And the computer calculates the entire equation all over again and says, well, if you change that, then this is your solution. And it does it over and over again really, really fast. So by the time you get to actually be an aerospace engineer, nobody is solving equations so much anymore, but they just know what the equation is supposed to do. And so here, hopefully it'll load real quickly. Come on. It's a little applet. And, you know, in real life, things would be more complicated, but let's see, what's this? I don't want that. Oh, it's not going to let me do it. All right, fine. So I was going to show you this little applet, which allows you to play with the angle of attack, the angle that this wedge is at, how wide is that wedge, and what the effects of the shock are. And you can just move around with different values of angles and speeds, and you can see what the effects are. And typically engineers like to colorize their pictures. So the reds might be where the temperatures are high or the pressures are high. The computer would tell you that. And the greens might be where the velocities or the pressures are low or something. You can't see it, of course, but so now how do I get back? Oh, let's see, let's try this. Let's try closing it. It was, but I got bored of it. Well, there's all kinds of equations I was still going to show you, but here's my favorite one. You'd think that people were done with jumping out of airplanes and buildings. Now that we have computers that can simulate what's going to happen, this guy, I just found this, he is going to take himself up into the stratosphere in a balloon. And he's going to jump out wearing a spacesuit. And he thinks he's going to fly at speeds or near the speeds of the speed of sound in a spacesuit. So I don't know if he's actually done it or if he's lived or anything. But it was a YouTube video, and he seemed very serious, and I saw his spacesuit, and it looks very real. But I was noticing all kinds of things about the design of his spacesuit. So for instance, his helmet is completely round, which is really the wrong shape if you want to be supersonic, right? And so I'm thinking, I think it's going to break his neck, right? It's going to pop his head off. But I don't know what's going to happen, and this thing is going to take forever to load. So. Boy. I don't know if it's going to work. All right. Ooh, if it loads, it loads. But that's the end of my lecture. I just wanted to say you don't need math. Unless, of course, you want to live. Or if you have a limited amount of funds. Or if you want to get it done in some sort of time scale. But if any of those things, well, then of course you're going to need some math. Yes, sir?
Did the Wright brothers have good math background, or do you know? Or?
They had some good math background. The Wright brothers were interesting. A lot of people had been trying to fly and even had flown before the Wright brothers. And what the Wright brothers really did is they introduced propellers to airplanes. So one of the Wright brothers, he was really interesting. They were both real good at making things with metal, you know, and hammers and stuff. So they invented this vane, essentially. It was a wing, an airfoil, and they mounted it vertically, so the airfoil curved in this direction, vertically, on a circular pedestal, I guess, and they put it on his handlebars of his bicycle, and he would angle it at a particular angle, and he would ride his bike really fast to see what angle was the best angle of attack to get the most lift. And so, as he's riding his bike, he would notice, whoa, that was a lot of lift, or that wasn't very much lift. And so they came up with the number 13 degrees, which after many years later, with some higher level mathematics, they realized that was the best angle. But you don't, like I said, you don't need these super huge complicated equations. You just need to want to do it. And then you make a plan, and if it has weight, how do you model that weight? You could make things to model the weight, an actual weight, or you could pretend something is a weight with a number. And the math is just a tool. You don't need it. You use it to the extent that it's helpful, right? But the more math you know, the better you can apply it as a tool to fix problems that you have when they come up. That answers your question. But yeah, the Wright brothers, they invented how to fly with a propeller. Any other questions, if you have them?
What's b squared in that equation?
B squared is, if you have a wing,
Excuse me.
I'm a bad artist. The wingspan, so this distance
It's a fence.
is B. So they use that as a calculation for area, which is more, the wingspan is more important than the width, the actual area of the wing. The width has not much to do with lift, it's the length of it.
Sure. So some of the planes now have the tips of the wings are bent up on the ends there. Not all of them, but some of the commercial airlines now have the tips.
You mean it's like this?
No, it's vertical. They
Just
come out, and then there's a little part that sticks up.
Oh, you mean on the end of the wing?
Yeah, on the end.
Oh, yeah.
Right.
Those prevent, okay, let's see. So, you know you've got this airplane and it has weight. So you have this airplane, and if you design the wings flat, when you're flying, you know, it's a piece of metal and it bends. So when you're flying, they kind of bow out a little bit. Or I did this in the opposite direction. They kind of bow out, I did it the right direction. They kind of do this sort of thing. I'm exaggerating, but when the air is pushing up on the wing, they kind of bend upwards a little bit. And the